In the previous video I showed you guys the Maho that I'm retrofitting and the Delta servo motor that I'm going to install on this machine. But there is one critical part that we haven't really talked about yet. How do you fit servo motors like these on a machine that were designed for entirely different motors? And that is what these adapters are for. And honestly, this has been one of the most challenging parts of the entire project so far. And in this video, I'm going to walk you through the design, the problems I had to solve, the decisions I had to make, and why I actually made those decisions. And at the end, I'm also going to need your help, because I want to make sure that I haven't missed something that might be obvious to someone else before I start committing to manufacturing these adapters out of metal. So let's dive in. But before we dive into the adapter design, there's one thing I need to address first. Axis naming. According to the original Maho manual, the Z-axis is the RAM, but I'm going to change that. From now on, the Y-axis is the RAM and the Z-axis is the vertical axis. Why am I doing this? Well, I've got a few reasons for this. First, I'll be using this machine primarily as a vertical milling machine. And in that configuration, Z is always the vertical axis. That is just the convention. Second, it just prevents confusion. Everyone I talk to expects that the Z-axis is the vertical axis, so it just makes conversations a bit easier. And third, it's gonna make my life easier when I'm working with CAM, because CAM also assumes that Z is the vertical axis. Now, this decision does have a consequence. I will need to update all my documentation. Thankfully, I have already rewritten the original manual in LaTeX, and I've also created the electrical schemas myself. So that's gonna be manageable. Before we get into the specific problems, I feel that I need to explain what these adapters represent to this project. These aren't just convenient bolt-on parts. These are fundamental to this machine. If an adapter fails, the entire machine is down. Period. Possibly even for weeks, or in the worst case even months. And the cost of getting these wrong is really high. A design flaw could lead to either damaged motors, failed bearings, a broken coupling, or in the worst case, a complete redesign and remanufacture of all these parts. So we are potentially talking to hundreds or even thousands of euros if all three adapters need to be replaced. And unlike with software, where you can iterate pretty cheaply, mechanical parts can only be tested after they are manufactured and installed on the machine. So I just feel that I need to be as thorough as I can in the design phase. I need to think through every aspect of this design carefully. And that is why these adapters have been the most challenging parts of this project so far. And that's also why I'm taking you through my entire thought process. So next up, let's look at the three main problems that we need to solve with these adapters. The first problem is pretty fundamental. The Delta servo motor and the original Incompatible servo motors use completely different mounting systems. The Incompatible servo motor uses a proprietary mounting flange with a specific bolt hole pattern and a pilot diameter, while the Delta servo motors, on the other hand, use a standard NEMA mounting pattern. These two systems are just completely incompatible. You cannot swap one out for the other. So right away we know we need some kind of adapter that converts this NEMA interface to the Indramat, or in this case the machine interface. The second problem is more subtle, but it's still critical. And I'm talking about the maximum radial load that the motor shaft can handle. You see, servomotor shafts aren't designed to carry large radial loads. They are designed to transmit torque. But in our case, we have a timing belt pulling on a pulley, and that creates a significant radial force on the shaft. If we look at the delta motor specification, we can see the maximum radial load listed right here. This is the maximum force that the motor shaft can handle without damaging the bearings inside the motor. Now, you might think, why not just use a simple adapter plate like this? Well, I think there are two problems with this approach. First, it pushes the pulley even further away from the motor mounting face, which increases the moment arm and makes the radial load problem even worse. And second, I have made some calculations here. I calculated the belt tension based on the torque we need to transmit and the resulting radial forces on the motor shaft. And the result is pretty clear to me. We exceed the motor's radial load limit by a significant margin. This drawing summarizes everything. The forces involved, the distances, and why I think a simple adapter plate won't work. If we were to mount the pulley directly on the motor shaft, especially with an adapter plate, I think we'd be overloading the motor bearings, which would lead to premature failure. And this is why we need an adapter that includes its own bearings to carry these radial loads, protecting the motor shaft from forces it was never designed to handle. And finally, the third problem, installation space. Now, this isn't equally critical on all three axes. Like, look at the x-axis. This space we have in depth, in width, in height, it's not gonna get any better than this. Trust me. The z-axis is a bit tighter, but it's still manageable. We have enough clearance to work with in all directions. Now there are some cables and some tubes in the way here, but yeah, I'd say in the worst case we need to move some cables around, which it's manageable. But then the y-axis. The y-axis is where things get challenging. As you can see, when I try to fit the motor here with the cable attached, the connector just simply doesn't fit. It hits this cover. Now, you might wonder, is the new motor really that much bigger than the original? Well, let's compare them. Here is the original Indramat motor with its cable, and here is the Delta motor with its cable. You can clearly see the difference. The Delta motor has a much larger profile than the Indramat motor. To be more exact, the Indramat motor is in total about 190-200 millimeters high, while the Delta motor is in total about 230-240 millimeters high. So that is quite a difference. So what's the solution? I'll get back to that later. Alright, so we have three problems we need to solve. Incompatible mounting systems, radial forces that exceed the motor specifications, and tight installation space, especially here on the y-axis. So let's have a look at the solution that I came up with. This is the final adapter design. You might be wondering, why is this so complex for something that's supposed to be just a mounting adapter? Well, let me walk you through how I got here. I started with what seemed like the obvious approach. a traditional adapter design with the bearings positioned in line like you see here. And functionally this would work, but there was something that just kept bothering me. With the bearings this close together, I just wasn't confident about the load capacity. I would have needed complex bearing calculations just to prove to myself it could safely handle the radial forces from the timing belt. So I spent a few months iterating on this design, running calculations and trying to convince myself the bearing spacing was adequate, but I just never felt fully confident about it. Then a friend of mine suggested something that turned out to be the breakthrough. What if we position one of the bearings around the flex coupling? And that's exactly what I did. One bearing sits around the flex coupling, while the other stays close to the pulley. This spreads the bearings further apart, which means they can handle the radial forces from the timing belt much more effectively. And as an additional bonus, it makes the adapter around 25mm shorter than the original design, and it makes more efficient use of the space around the flex coupling. With the bearings spread further apart like this, I have good confidence in the load capacity without needing any complex calculations. Now, you might remember from earlier that the y-axis has a specific challenge with the motor cable connector hitting this cover. With my initial design, I attempted to work around this issue by putting the motor at an angle so the cables stick out to the side. But that solution felt meh, because this would make the adapter for the y-axis different from the other two axes, and it would leave the cables exposed on this side of the RAM, which just isn't ideal in such an environment. So instead, I wanted to make all three adapters identical, which is also better for documentation, manufacturing, and maintenance. And since the problem is with the height of the cables, see if I can just lower this cover instead. So let's remove this cover and see if we run into any other issues. I've got one adapter that has the motor that installs the motor angled, and this adapter will install the motor straight, so I'm just gonna switch these two prototype adapters. It's pretty cold in here, so my fingers are getting a bit numb. You might be asking, why is he twisting it? Well, I've got two inserts here, and I prefer to have them vertically instead of horizontally, just because then it's a little bit stronger. We're still working with plastic, so it's probably strong enough, but you can never be sure enough if you have an expensive motor that you're working with. As you can see, with the cover removed, there is enough room for the motor and the cables, but let's hope I didn't miss anything that's gonna bite me in the rear afterwards. I do already know about one thing that will need to be changed, because the display was actually mounted right here. And that won't fit anymore because it went all the way in, and yeah, that's just not gonna fit anymore because of the cable. But I'm willing to accept that problem for now, and I will just figure that out when I get to it. You know, one challenge at a time. For now, oh, now that I look at it, if I look at this at this distance and the spindle here, there is one thing that I would like to check at this moment, and that is whether whether one of these cables will touch the casting before we hit the hard stop on the back. So let's move the axis in and keep an eye on the cables right here and here in the back. And let's see, this is where the hard stop is. I cannot move any further. It's hit the hard stop on the other end. So that is actually very good news, especially since we do have enough room here, which is a good thing. But actually the new design is already 25 millimeters shorter than this design. So it looks like this is actually going to work out, which is very nice. Now let's take a closer look at the final adapter design and walk through some of the key decisions. First, the interfaces. On one side we have the NEMA motor mounting pattern for the Delta servo motor, and on the other side we need to match the Indramat mounting pattern that the machine expects. Getting the bolt patterns right is pretty straightforward. But I would like to get some advice on the tolerances for this pilot diameter for the motor side. I could just specify a 0.01 millimeter tolerance, but that would make manufacturing extremely expensive on this diameter. I could also go with a 0.1 millimeter, but that feels too loose for a proper connection to the flex coupling. So the question is, what's realistic here without breaking the bank? For the bearings themselves, I chose standard lifetime lubricated ball bearings. The big bearing costs around 100 to 110 euros and the small one about 10 euros. So this will always be cheaper than building a whole lubrication system, which is what I think I would need to do if I would use other types of bearings. Now, I did find a much cheaper version of the large bearing from no-name brands, but I decided not to take that risk. These bearings are too critical to the entire machine to save 80 or 90 euros and potentially regret it later. Now let's have a look at how these bearings will be mounted. The large bearing has its inner race held in place by a clamp ring, while the outer race is actually floating. And I did this because I think it accommodates for thermal expansion and manufacturing tolerances in the axial direction. At least that is my theory. I'd love to hear from anyone with experience if this floating outer race design is actually a good idea or if it's going to bite me in the ass later. The smaller bearing has its inner race secured by a lock nut and the outer race is held by a Kirkclip. This is actually the only place so far where I'll need to buy an extra tool specifically for mounting this lock nut. And if anyone has experience with this, I'd appreciate any advice on what I should keep in mind when mounting this bearing, like what torque to put on the lock nut. And while I'm asking for help, this is also where I could really use some guidance on the tolerances for the bearing seats. Getting these wrong could mean the bearings either don't seat properly or have too much play. So If you have experience with this, please let me know in the comments. Now, let me talk about what was probably the most significant design change I made, and one that came way too late. I originally designed this adapter around a single disc flex coupling, and since they were at a discount at the time, I already bought them for each adapter. And since they were at a discount at the time, I bought one extra in case one might fail. But then I actually read the specifications more carefully. This coupling can only handle 0.02 of a millimeter of lateral misalignment, is in this direction. And that's only 20 microns, essentially perfect alignment. And here's the problem. Even the motor itself has manufacturing tolerances that exceed those 20 microns. The motor shaft position tolerance alone, as I show here, is already larger than what the coupling can handle. So even when all the other parts of the adapter would be made perfectly, which doesn't exist in the world, this is not the correct coupling for this application. So I decided to switch to this double disc type flex coupling, which brought two major advantages. First, it can handle 0.3 of lateral misalignment instead of 20 microns like this one. That's 15 times more forgiving. Suddenly, this actually becomes manufacturable within realistic tolerances and costs. And secondly, the diameter is actually smaller, which might not sound like a big deal, but it is. With a smaller coupling diameter, I can get a smaller hub around the coupling and a smaller bearing around this coupling. This significantly reduces the rotational inertia of the entire assembly, which means less torque is needed to accelerate and decelerate. And for our servo system, that just matters. Now, there is a downside to this change. I will have to order new, more expensive couplings, and the ones I already bought, they're just gonna be sitting here useless, and that's just annoying. But the alternative, trying to hold impossibly tight tolerances, or worse, having a coupling fail during operation and damaging the adapter or the motor, that would be far more expensive, and it might even lead to a complete redesign and remanufacture, and that's just a failure mode I really want to avoid. So now that I've shown you the design and walked you through my thought process, this is where I could really use your help. First, am I missing something obvious here? I have been staring at this design for weeks now, and sometimes you just need someone else to catch what you've overlooked. Second, all those tolerance questions I mentioned throughout, like the pilot diameters, bearing seats, the lock nut torque, whether that floating outer race is actually a good idea. If you have experience with any of this, please share it in the comments. And third, I'm currently not able to manufacture these precision parts myself because, well, I don't have a working milling machine. So if anyone from the community is willing to help out with the machining of these parts, I'd love to hear from you. Now the question is, where do I go from here? I've already made this exploded view and animation to verify the order of assembly and make sure all the parts actually fit together. But to really confirm this, I will be 3D printing all the parts of the new design, which lets me catch any final assembly issues within the adapter and on the machine. After that, I need to create detailed manufacturing drawings with all the GD&T tolerances, and hopefully I can get some help from you with some of those tolerance decisions. Once the drawings are done and I found someone to make the parts, I'll start with a single prototype adapter. Test it and make sure everything works as expected. And only then order the parts for the other two axes. Then it's assembly, testing, and hopefully, finally, getting these motors mounted and running. I'm not sure whether these adapters require the most challenging design for this entire retrofit project. They might look simple, but getting them just right requires thinking through a lot of details. If you think you can help with any of my questions, please let me know in the comments. I really do appreciate the input. And if you are following along with this project, thanks for sticking with me through this deep dive, and I'll see you in the next video.